Assalamu alaikum students, I am your course instructor Muhammad Kashif and the course name is Design and Analysis of Algorithm. In today's lecture we are going to explore further more examples related to the BFS and DFS algorithm. And as you know, in previous lecture we have covered or we studied these two algorithms, breadth first search and depth first search algorithm. So in these two particular algorithms we solve our problems related to the graph theory, and you've seen that we have multiple nodes, we have multiple networks, we can have multiple computers that wants to communicate with each other. And when we need to solve or when we want to access from one computer to another computer, obviously we have algorithms to access those adjacent nodes, or you can say the adjacent computers. Obviously we consider the adjacent nodes as communicating devices, because whenever we transfer files, whenever we move data from one computer to another computer, then definitely there must be an algorithm that support of that particular movement, right? So for particular graph theory or the graph related problems, we can solve or we can implement these problems by using breadth first search algorithm and depth first search algorithm. In breadth first search algorithm, you have seen that we used queue data structure to implement our BFS problems, and when we talk about DFS algorithm, we just simply use a stack data structure to implement our problem. In queue we focus on first in first out approach, because what the data comes first, that will pop up first, and then obviously our queue will give us the direction of data movement. And when we talk about the DFS algorithm, stack data structure guide us to move data, or it tells or it gives the direction from one node to another node. So this was all about the last lecture. In today's lecture we are going to explore more examples to understand the functionality or the process of BFS and DFS algorithm. Alright students, to understand BFS and DFS algorithm, we are considering more examples to clarify the process or the method of this algorithm. So first of all, I'm going to write an algorithm for BFS. For this particular example, you can see we have multiple nodes in this fashion. Obviously we have 3, we have 4, and we have 5th node, and we have 6th node, and then we have 7th node. And we need to connect all these nodes, because without connection we cannot move or we cannot perform communication between these nodes. So here we have edges between each node. That means all the nodes are connected with some nodes, and this is basically a graph. And now we are going to use, or you can say to solve this problem by using breadth first search algorithm. So breadth first search means first of all we need to understand what type of data structure we are going to use here, and that was FIFO, and queue operation would be performed over here, right? So first of all, obviously we are using queue data structure, and how we can insert the data elements into our queue. So we have to make an adjacency list on each node. Like if we are here, and I told you in previous lecture, we need to define or we need to identify our root node whenever I am implementing BFS or DFS algorithm. So let's say we have 1 as a root node, and you can choose any one of the nodes from this graph. So I'm selecting 1 as a root node, so because I'm starting from 1. So here I want to update my adjacency list. So 3 and 2 are the adjacent nodes over here, and obviously I am using queue, right? So first in first out data structure would be used over here. So For this particular reason, I'm going to insert my first node, that is 1, because I visited or I explored this node. Explore means I updated all the adjacent nodes that are directly connected with 1, right? So 3 and 2 are basically connected with this node. So when you find the adjacent nodes of any node in BFS algorithm, you should have to update all the new data elements in a queue, in your array, right? So you can use any order. As I told you before, you can either place 2 or you can place 3 first and then 2. You can choose any order, right? So by choosing different orders, you will get a different path, right? So this is already I mentioned in my previous lectures, right? So obviously I am performing FIFO first in first out. So I entered my 1 for the first time. So this will be popped first, and then I will move to my next node. So when I pop this element from the array, or you can say the queue data structure, then that means I have a variable named result, and I will update my result, right? Because I've got 1 from my data structure, I have got 1 from this queue, right? Because I pop this element from this array, right? Now I need to move on my next element, and who will tell us? Obviously the array, the queue data structure. Now 3 becomes a first element at this time, right? That means I need to move from 1 to 3. That means I traverse my graph from 1 to 3. So here I am, place a dotted line over here because I want to move from 1 to 3. So this means my direction would be from 1 to 3. So here I have to check, or I need to know the new adjacent nodes are available here or not. And obviously we will get new nodes here because 3 has multiple adjacent nodes, like 3 has 1 adjacent node, 3 has 2 and 4, and we can move towards 5 from 3, and we can move towards 6 from this particular node. So these are the adjacent nodes that are available or that are directly connected with 3, right? So now we need to check what elements are already available in my queue. So 1 is already placed in my queue, 2 is already placed in my queue. Now 4, 5 and 6 are the new data elements I have found here, because 1 and 2 were already placed in my queue. Now I need to push these 3 new data elements in my queue. So 4, 5, 6, you can choose any of the order. You can place 5 first, or you can place 6 first, and then you pick up 5 and 4. So if I choose, if I enter 4 first and then 5 and then 6, so now I obviously discover, or I visited this node, that is 3. So I need to pop my element, that is 3. Pop means I am taking this number as a result, right? So I am storing, or I am saving my data element that is available on top of the queue, because 3 was the first element that is available in a queue, because I am deleting these nodes from my queue, right? So now my next movement, my next data node, that would be 2, because the first element would be 2, because in this particular example we have 2 data element that is available now. So I want to move on my next node, that is 2. So my movement from 3 to 2 would be like this. So I'm I want to move from this node to any adjacent node, and my queue is guiding me to move from 3 to 2. So my movement would be from 3 to 2, right? So here I want to explore the adjacent nodes that are directly connected with 2. So here I visited this node, but I need to know the adjacent nodes of 2. So here we can see that 1, 3 and 4 are basically the adjacent node of this 2, right? So I need to check whether these data elements are available in my queue or not. So 1 is already there, 3 is already there, and 4 was already there. So obviously all the data elements are already placed or stored in my array. So no new node has been found here, or you can say we cannot explore any new node that is available on this node. So all the data elements are already available in a queue. So that means we discover or we visited this node. So I need to pop this element from the queue, and I want to store this element in a result variable. Right now I need to move on my next node. How can I move on my next node? My queue will direct you or give you the direction, and now I have to move from 2 to 4. That means my direction would be like this. I'm moving from 2 towards 4. So now I'm here at this point. I visited this because I'm here and I want to update my adjacency list. So the adjacent nodes are 2, 3 and 5. So these 3 nodes are adjacent, or you can say we have the 6, right? 2, 3 and 6. So these 3 data elements are directly connected with 4. So we have to check whether these elements are stored or placed in our array. So 2 was already there, 3 was already there, 6 is already pushed into a queue, right? That is available in your queue. So now I need to pop this element from my queue. So I am going to take a print of this 4 because I visited this node, right? So now I need to move on my next node. Where should I move? Where should I go to explore my further new nodes? So here we can see that we place 5 here. So I want to move from 4 to 5. But obviously, how can I move from 4 to 5? Obviously, my queue will guide me to access this node first. So obviously, my next node would be 5, because I cannot move from 4 towards 6 because 6 was inserted later later on this node. So first of all I need to visit this node. So that is 5. So I'm here now. I need to update my the adjacency list. So 5 is directly connected with 3, 5 is directly connected with 7. So these are 2 adjacent nodes that are directly connected with 5, but 3 is already inserted in my queue, and 7 is not available. So I need to push, or I need to insert the 7 in my queue. So this is a new node that I discover or that I explore when I am on this node. So now I want to check, or I want to explore further new nodes or unvisited nodes. How can I do that? Obviously by popping my element, and I'm going to pop 5 and use this 5 as a result variable, or you can say I'm storing or I'm saving this data element in my result variable. Now I need to move on my next node, and that is 6, and that means I'm going here because queue giving me a direction to move on my next node, and that is 6. And if I am here, I have some adjacent nodes. 3 and 4 and then 7 are basically directly connected with this node. 3 is already placed in my queue, 4 is already available, 7 is already available. So these nodes are already available in my queue. So no new node has been discovered. Now I need to pop my element, and that would be 6, right? So now I want to move on my next node, and only 7 is left in my queue. So obviously my queue giving me the direction from 6 to 7. So I will come here and check whether the node is visited or not, and obviously it was unvisited because we did not mark it as a visited. So when we reach here, or when we access this node, we can see that 5 and 6 are the adjacent nodes that are already available in my queue. So no new node has been discovered. So if that means we visited all the nodes that we want to explore, or that we want to access in this particular problem. So here now we are going to pop this 7 from the queue. So you can see that we have got a path by using breadth first search algorithm, and if you use multiple, or if you want to get different paths, you have to use different combinations. Like here we can use a combination of 6 6 5 4, and or either you can use a sequence of 5 4 6, but we had used 4 5 6, right? So these were the places where you can choose, or you can enter in a different direction or in a different order of these data elements to get a different path. And obviously we already discussed that graph gives you multiple paths, graph gives you multiple solutions, and only one solution cannot be possible, or you can say we cannot get only one solution or one path in graph theory while we are implementing breadth first search or depth first search algorithm. Now we are going to solve same problem by using depth first search algorithm for DFS. We are again going to use the same problem, and we will see that how our paths would be different from the same problem, right? So we will see our solution. So obviously we have the same problem, we have 7 and we have 6, right? So we are connecting these nodes with each other, and in a manner in which we can send the data from one node to another node. And obviously we want to access these nodes because each node contains data, each node contains files. So because we cannot access the data elements, or we cannot access the content until and unless we reach out these locations. Or you can map this problem with your, you can understand this problem by taking example of mobile communication. These nodes are just like your mobile phones, and they want to communicate with each other, right? So how they can access the data, or they perform communication from one network to another network? Obviously there are graph theory that we are going to study, or we are exploring. And but now here we have an algorithm that is called depth first search, and by using depth first search we are going to implement this problem. And in DFS you have seen, or we have already studied, that we explore or we visit all the adjacent nodes in one direction, or you can say we will use a stack data structure in which we will place our data adjacent data to the stack. And how we will move from one element to another element, definitely on the basis of adjacent nodes, but there might be chances of backtracking, there might be chances of deadlock, because in BFS algorithm you have seen that we do not move from one node to the previous node, but in DFS we can do that. And obviously we are going to use a stack data structure. We have already studied in previous lecture, and in stack you used LIFO operation, last in first out operation. For this purpose we are going to draw a stack structure here, And obviously in DFS algorithm we are again assuming our root node, and obviously I already told you so many times you can use any node as a root node. So I am going to make this node as a root node. So first of all I am going to mark this node and I am going to push this data element into my stack, right? So now I want to update, I have to update my adjacency list over here, because 1 is directly connected with 3 and 2, right? So but in DFS algorithm you will not update, or you will not push these data elements in one go. You have to push only one data element, either it could be 3 or it could be 2. But in BFS you have seen whenever we got adjacent nodes, we enter or we insert all the adjacent nodes in one go. But DFS algorithm is different from BFS. In DFS we just pick only one node, and only one node would be inserted, or you can say push into the stack first. So obviously we already push 1 in my stack. Now I want to move from 1 to 3, or either I can choose this path, I can move from 1 to 2. So I choose 3 to move here, right? So if I move from 1 to 3, so I need to, you know, push this number or push this node in my stack. So if I'm here, I obviously perform again the adjacency list. I will update my adjacency list, or I can see that 1 and 2, 4 and 5 and 6 are basically the adjacent nodes that are directly connected with 3. But obviously I can choose only one node to push the data element into the stack. So here if I choose 2 to push, so 1 was already there, 1 was already pushed into the stack, so I cannot push this 1 into the stack. So if I choose 2 to move or to, you know, traverse my problem, that means I am going to push this 2 into the stack. That means my direction would be like this. I can move 3 towards 2. So when I, you know, move towards next node, I mark the previous node as visited, as I mark here, and I mark 3 as visited node. And whenever I reach out to my next node, I have to update my adjacency list on each iteration. So here I can update my adjacency list. You can see that 1, 3 and 4 are basically the adjacent nodes of 2. And obviously on each iteration I need to check, I have to check my adjacency list. I need to compare this adjacency list with my stack. So 1 is already there, 3 is already there, 4 is not available in my stack. So obviously I can choose, or I can move from 2 to my next node, and that would be 4. So that means I need to push this new data element or new node in my stack. So I reach out and I am going to mark this node as visited. So from this node I come here, I access this node, so I again will update my adjacency list. So here I can see that 3, 2 and 6 are basically the adjacent nodes, right? So 4 has been visited, but I need to compare my adjacency list with my stack. So 3 was already there, 2 is already there, 6 is not available in my stack. So I'm going to, you know, place the 6 in my stack, right? So that means my movement from 4 to 6 would be like this. So now I'm here, so I need to update my adjacency list again. I can see that 4, 3 and 7 are basically the adjacent nodes of 6. So this is the adjacency list, but I need to compare this adjacency list with my stack. So 4 is already available in my stack, 3 is already available in my stack, but 7 is not there, right? So I need to push this data element into the stack. So I'm going to push 7 in my stack, right? So according to this phenomena, I will move from 6 towards 7. So I'm here now, I need to update my the adjacency list, right? So if I reach out, so I need to update the adjacency list. So 5 and 6 are basically the adjacent nodes of 7, but 5 and 6 is already there. 6 is already available in my stack, but 5 is not there. 5 should be visited, or 5 should be pushed into the stack. So I'm going to make another memory location in my stack. So here I am going to push the 5, right? So because I found this new data element from the from this node, right? So 7 has been visited, and I can access 5 from the 7, right? So when I reach out here and I already push this data element into the stack, that means this node has been visited. And as a result, you have seen that we are going to take print, or we are going to get these data elements in as a result. So I'm going to print 1, 3, 2, 4, 6, 7 and 5 in this manner, right? And I'm using a depth first search algorithm, and here I want to check whether I'm getting the new data elements or not. So I have to update my adjacency list. So here we have 3, we have 7, but 3 and 7 are already available in my stack, so no new data element has been found here. So that means all the nodes have been discovered, or all the nodes have been visited, right? Because all the nodes have been marked. But we can see that because we are human beings, and we can see this graph has been traversed, or you can see this graph has been visited all the nodes by using depth first search algorithm. How a computer will know that? How we make sure that the all nodes have been visited? Because computer cannot understand the terminologies or the language that we are using, that only check, because computer check each data element again and again by using pop function. So because we are here and we push 5 on the top, or the last element is basically 5, because we are moving from bottom to up, and the 5 element is basically your last element. So now we are going to pop this element from this location. Pop means we are deleting this element. So our pop has been updated, our last element has been updated now. So here we are backtracking, and when we are at 7th position, computer will check whether we are getting new data element or not. So we are not getting the new data elements because 5 and 6 are already available in my stack. So obviously we need to pop this element too. So we are going to pop this element because we are not getting the new data elements on this particular node. Now the last element has been updated, and by using backtracking we will reach out here on 6. Do we have a new data elements? No, we do not find, or we do not get new data elements over here. All the nodes have already been placed into the stack. So we are going to pop this element, right? So we pop this element again, and my last has been updated now. So I will go back from 6 towards 4. Right. So here do we have a new node over here? No, we do not have any new node found here. So we are going to pop this element as well, right? So we popped out, right? And where should we move? We should move from 4 to 2, same direction that we used to access 4. From 2 to 4 we can backtrack from 4 towards 2. So here our last element has been updated now. So 2 becomes the last node, becomes the last data element, but here we do not found any further new node. So here we need to pop this element. This is basically a check. This is an additional condition that computer satisfy whether it traverse or whether it discover all the it visited all the nodes or not. So our last has been updated now, so 3 has become the last element. At point 3 we couldn't find any new node, so we can say that 3 should be popped now. So 3 has been popped now, so our last has been updated now. So at position 1 we can see that we cannot find, or we do not have any new node over here. All the nodes are already placed in my results, or was already there in my stack. So we need to pop this element as well. So you can see that each node has been popped from the stack. That means stack has been empty now, and this is the termination condition of this algorithm, because stack is empty now. And if the stack has even a one single element, we will move towards that particular element from a specific node. And when the stack has been empty, we can say that we cannot move further more, and we cannot access my next node or further more nodes. So our algorithm will be terminated here. So this was the depth first search algorithm. And you can see that if we compare this algorithm with BFS, so you can see that we have a path 1, 3, 2, 4, 5. 1, 3, 2, 4, 5, right? And I'm going to place all the numbers to compare my path. And you can see that this is the solution of DFS, and this is the solution of BFS. And you can see the clear difference over here. We've got a different path. In DFS we've got 1, 3, 2, 4, and same path we've got here, because unfortunately we use the same nodes. But here you can see that 6, 7, 5 are the nodes or the path that we've got from DFS, but in BFS we've got 5, 6, 7. So the order has been changed now. So this is the difference between BFS and DFS algorithm. Both the algorithm can be used to generate or to get the solution or to get the paths where we can move, or where we can allow the data communication from one node to another node. Now you can map this problem to any kind of real life problems that are related to transportation system, that are related to the Google map. You can use Uber or Cream. They are using your locations, they are accessing the roads. Obviously when you move from your home to your office, to your university, there must be an edge, there must be a road connected with your source node and to your destination node. How you move, or how a software calculate your fares, how a software calculate your positions or locations, obviously there is a graph theory, and we use BFS or DFS algorithm to implement these problems. So students, we have used a problem, and we run BFS and DFS, both the algorithms, on a same problem, and you have seen that we've got different paths, we've got solutions, right? And obviously we already studied in graph theory. We have connected graph, we have paths, we have cyclic paths, or we have directed graph, right? So on that particular examples, you can see that we get different solutions, and on each path or on each solution we will get multiple number of nodes, multiple devices that can communicate with each other. And you have seen that we've got two multiple solutions, and in each solution obviously there are nodes, there are multiple computers, there are multiple devices which can be communicated with each other, right? So you can use these nodes as a computer, as a mobile, as a buses, as a car, as any vehicle or any network device that can be used to transfer the data, that can be used to fetch the data. So as I already told you that we implement our real life problems in which we use graph theory, and graph theory solve our daily life problems in which we are sending, receiving data. We are solving our lots of problems in our real life, whether we are traveling, whether we are selecting multiple things, whether we are sending the data to multiple nodes in one go, or whether we are calling from one mobile network to multiple mobile networks. We are doing chatting by using WhatsApp, we are doing chatting via Facebook. So that are all the application areas where we can see the graph theory implementation. And when we talk about graph theory, so definitely we want to reach out those nodes where we should, or where we can get the data, or where we can store the data, right? As you can see that we have a lot of servers available. We have cloud computing, where clouds are basically servers, clouds are basically computers that are using to provide us the data, and we are basically the computer users who are connecting with thousands of servers that are available in the world, right? So even you can say the millions of servers that are facilitating us to provide the data, right? And whenever you search anything from the Google, that gives you the direct data, and Google render all the data from multiple nodes, from millions of servers, how they are providing the data, how they are accessing you can access those servers. Obviously there is a graph theory, there is a mechanism, there is a solution, there is an algorithm that is implemented behind of this complex problems, right? So this was today's lecture, in which you learn how we can implement BFS. And in BFS you have used queue data structure. In queue you have a process in which you enter the data, or you pop up the data from the queue in a fashion that is called first in first out. But when you implement the depth first search algorithm, in depth first search algorithm you implement stack data structure. In stack data structure you have an operation that is called LIFO, last in first out. Whatever you are pushing the data element into the stack, and that would becomes a last element, and that should be pop first, and then you can move towards the next data element. And you have seen that in DFS we have backtracking, we can move towards back that is already explored, or that node that is already visited, right? But in BFS you just simply use a queue data structure in which you can move, or you can traverse your graph or your problem by using FIFO operation. So this is all about today's lecture. Thank you so much. If you have any question, you can contact me.